All right, so today we're going to talk about the precise definition of a limit. And the purpose of this section is to kind of, it's a way of proving that limits exist. Okay, so I know that as far as the AP exam goes, this stuff you're not responsible for, but you know, we don't teach to the AP. I mean, we're learning calculus here, so we're definitely going to cover this. And you're definitely going to see this in Calc BC again to a greater extent. So it's actually good that you're exposed to this. So, you know, let's just quickly write what the goal to this section is. And the goal of this section is to show how a proof can be constructed to prove certain limits exist. And of course, there may be instances where the limit does not exist, and I'll show you exactly how this definition of a limit works. Okay, so let's define, let's actually give this the precise definition of a limit, so then we can go ahead and show what the idea behind this is and what the motivation is. We'll show it visually first. I'll show you exactly what's going on visually, and then algebraically we'll go ahead and prove an example, and that'll basically wrap up this section. Okay, so we're going to define this as let f be a function defined on some interval, on some actually open interval that contains the number a except possibly at a itself. Okay, so except possibly at a itself. And remember, we don't really care what happens at a. We care what function, what y value this function approaches as we get close to a. So then we say that the limit of f of x as x approaches a is L. And we write it as, we write the following: the limit as x approaches a of f of x equals to L. Okay, and so this is basically what a definition of a limit is. So as far as the proof goes, to prove a limit exists, here's what we're going to do. We could also say if for every number epsilon greater than 0, and by the way, this is the Greek letter epsilon, so it's spelled epsilon. And these limit problems are usually known as, or these proofs, they're known as epsilon-delta proofs. So basically, we're saying, look, grab epsilon and let epsilon be some distance and greater than 0. And when we say greater than 0, that means we want it to be slightly larger than 0. In fact, it's an arbitrary number, but it's just some number that's greater than 0, but we want this number to be as small as possible. So we want to make this arbitrarily small. And you'll see that the smaller these numbers become, the more likely we are to have some problems if limits don't exist. So when you say if for every number epsilon greater than 0, think about epsilon as being some very small positive number. Okay? Then we could say there is a number delta greater than 0. So once again, this is the letter delta. And this is also something else just like epsilon. It's going to be some other number that's slightly positive. And the good news about delta is, or our goal is, we want to pick what delta is going to be. Okay, so whatever epsilon is, we're going to base delta off of epsilon, which is kind of nice because if epsilon's a small number, we'll come up with a relationship where delta kind of is a small number itself, but it could be written in terms of epsilon. So, and you'll see what I mean in just a minute. So, such that the following have to be true. Whenever the distance between f of x and L is less than epsilon, whenever x minus a is less than delta. So here's actually the important part. See, our goal is basically, this is the whole big idea. Okay, so what are we saying here? We're saying if I take some x value and I find a distance between x and a, and remember, these are my x values, right? This is what my limit is approaching. If I come back up here, notice how limit as x approaches a, f of x has to equal to L. So what I'm saying is, if I pick an x value, where when I take the distance between x and a, that if that's less than delta, then we also need to show that the y value at x minus the value that my limit supposedly approaches, this distance has to also be less than epsilon. If this is true, then we're basically saying the limit exists. Okay, so basically our goal is to manipulate this to show that the limit exists, is to manipulate delta in a way. We need to pick delta so that if this is true, then that's also true. And if we could show that this is true, then we're basically done. So here's what we want. We kind of start off with this. We want to pick a delta such that basically this is always true. Okay, so that's kind of what we're doing. I want to pick a delta where if this is true, then this is always true. And once we could show that, then we're basically done. Okay, so for our proof, this is what we want for our proof. So this is what we will use in our proofs. Okay, so let me show you visually what's going on, and then we'll do an example, and that basically will wrap this up. So here's a picture of what we're trying to do. So if I have, let's say we have some function that looks like this, and that's a. Okay, clearly we know in this class that the limit as x approaches a of f of x exists. Okay, so let's actually call this L. So we can say down here, we can say, look, clearly the limit as x approaches a of f of x, it does exist, and it is L. So let's see how the proof that we talked about earlier, how this works the way it does. Okay, so what are we doing? We defined epsilon as some positive distance. Okay, so what we did is we said, look, let's pretend that the distance from L to this random value I drew, this is epsilon. And since we're talking about distance, I need to go in both directions. So this is epsilon. And notice how epsilon is greater than 0. Okay, and if I draw this off and I kind of make a cutoff, what I notice is when the bottom part of this epsilon, or when this distance ends here, the x value there is whatever this is, and then we have another x value which puts us down here. Now, notice how these intervals are uneven, right? When I went across and I came down, the distance from a to this x value is much greater than the distance from a to this x value. And see, the smaller our deltas are, the better off we are, because if the limit doesn't exist, our definition or the proof that we're working with, things are going to go wrong for smaller deltas. So from these two, what I'm going to do is I'm going to call this distance delta. And if I'm calling that distance delta, then I'm actually going to go the same distance to the right as well. So we're rejecting the larger distance, okay? So here's what's happening. This is delta. So notice how if I go back to our definition, what are we saying? If I pick any x number or any x, so what's kind of like our condition here? If basically we say pick any x such that the distance from x to a is less than delta, which visually speaking, what do I want? If I want to pick an x where the distance from x to a is less than delta, what does that mean? Any x I pick in here will work. So I can't go outside. See, if I pick this x, what's the problem? From x to a, the distance from x to a is actually greater than delta. So I need to make sure that my hypothesis is satisfied. So what I need to do is just pick any x value in here. So let's say I pick this x, okay? Now, if you look at this x, the distance from x to a is clearly less than delta. So if this is satisfied, then what must be true? Then we know that the distance from f of x minus L better be less than epsilon. Now, if this isn't true, then we're running into a problem, or that means the limit doesn't exist. But we all know that this limit should exist, so this shouldn't fail. So look at what happens. It says whatever x you picked, as long as you're within delta, then you need to find f of x. So how do I find f of x? Well, if I come up to the graph, f of x is right there, right? Of course, at this x value, that's the corresponding y value. Now look, what's the distance between f of x and L? The distance between f of x and L is actually that red line that I drew. And notice how that red line, or that red length, is less than epsilon. And so you could see that no matter what x I pick, as long as it's within delta, where this x minus a is less than delta, f of x minus L, which is the distance from f of x to L, is always going to be less than epsilon. So notice how this is kind of a way of proving that a limit exists. Okay, so this is kind of like a visual of what's going on. We haven't really talked about this algebraically, and I'll show you guys how that works in just a minute. But what I want to do now is we could basically now kind of give you an example, and why don't I kind of summarize this in words just so you have it for future reference. So we could say, look, notice that for every epsilon greater than 0, and this is basically just some length positive that's greater than 0. So we're saying, notice that for every epsilon greater than 0, we can find a delta, which visually we kind of found the delta. I'll show you how we'll find delta algebraically in a minute. We learn how to find a delta such that the window, and I'm calling basically this right here, what I created, the window. So that's my window, right? So such that the window captures the graph. So in other words, I kind of have no gaps and so on. And what's important is also notice x minus a is less than delta implies if this is true, then we see, and I showed you this visually, and we talked about this, f of x minus L is less than epsilon. And that's the key. We noticed if x minus a is less than delta, then f of x minus L is less than epsilon. Okay? So what happens if a limit doesn't exist? How does this definition fail? Or how does this statement fail? So let's take a look at an example. So what I'm going to do is I'm going to do something like this. So clearly, at x equals a, my limit doesn't exist. Okay? So let's use the epsilon delta proof, or visually kind of talk about this, and then we'll talk about this algebraically. So let's call this L for the time being. So if we're trying to say, for example, the limit as x approaches a of f of x exists and it's L, let's see what goes wrong with it. So if this limit actually does exist, what would happen? Then we're claiming if you pick any epsilon, so notice if I pick this to be epsilon, okay, and remember the smaller the epsilon, the better off we are, but I think this is small enough, which will prove the point as to what's going on. So if this is my epsilon, notice how if I kind of draw my window, what's the problem? Remember how I found the delta? I found out where these epsilons intersected the graph, and then I went down and I took the smaller of the two deltas. Now, we could already see a problem. This epsilon doesn't intersect the graph. So right there, we could see that this window is going to have some breaks or cuts in it, which kind of is going to contradict what's happening. Now, look, this epsilon intersects this curve down here, so I could come down here and say, look, well, you know what? I don't care if it doesn't intersect it up here. It intersects it down here. So let's call this distance delta, which means I also have to go the same distance to the right. Let's call this delta. So here's what we mean. By definition, if I pick any x within this delta, my hypothesis will still be satisfied. So let me pick this x. All right? And what do I notice? The distance from x to a is clearly less than delta. So notice how if x minus a is less than delta, then we need to show that f of x, or if this limit exists, then f of x minus L should also be less than epsilon. But here's the problem. Where's f of x? F of x is somewhere up here. Now, what's the problem? F of x minus L is actually this distance, right? That's f of x minus L. And hopefully you could see what the problem is. This length right here, if we take a look at this length, the purple length right there, is epsilon. And clearly the red length, which is f of x minus L, is greater than epsilon. So what do we notice? If this is the case, but the problem we run into, f of x minus L is not less than epsilon. We could see visually. So what does that mean? This limit does not exist because it fails. Our hypothesis was satisfied, but our conclusion failed. And if your conclusion fails, then that means we have no such limit. So this limit doesn't exist. So visually, hopefully you see what's going on. Now, let's do an example where we are going to literally pick delta on our own. So here's our goal. If we want to show a limit exists, we need to pick such a delta, and we need to show, or we need to say, look, if this is true, then we need to show that f of x minus L is less than epsilon. Now, one thing I'll tell you is, the way I like to approach these problems is I always like to do scratch work first. My official proof, to be honest with you, is going to be very, very short. But the most important part is the official proof. So the scratch work is actually going to help us put the whole proof together. Okay, so whether you do the scratch work or not, I would highly recommend that you do use the scratch work because it just helps you organize your thoughts. And then you'll see that actually 90% of your official proof is just going to come from the scratch work. Okay, so here's what we want to do. We want to prove that the limit as x approaches 6 of x over 4 plus 3 equals to 9 over 2 by using the epsilon delta definition of a limit. Okay, so notice how we're basically just grabbing, and by the way, I'm trying to show that this is actually 9 over 2. So to do this, what we need to do is, here's what we want to show. So we want to show that for any epsilon greater than 0, there exists, remember this reverse E means there exists, so this means there exists a delta greater than 0 such that if x minus a is less than delta, so this is kind of like the hypothesis, we're assuming this to be true, then we need to show that f of x minus L is somehow less than epsilon. Okay, and that's kind of, this is the hard part. So here's what I want to do. Our goal is to somehow pick a delta where if x minus a is less than delta is true, then somehow we'll have f of x minus L be less than epsilon. So here's the thing. Since it's up to us to pick a delta, we're going to pick delta to be in terms of epsilon, because I somehow need to introduce epsilon. So what'll happen is delta will be kind of like a ratio of epsilon. So we'll say whatever epsilon is, I want delta to be a third of epsilon, or I want delta to be a fifth of epsilon. And then your question might be, well, how do I know what to pick delta to be? How do I know if it should be 1/2 epsilon, or 2 epsilon, or a third epsilon? And the answer to that is simple. Through my scratch work that I'm going to show you, we're going to figure that out. So here's what's happening for the scratch work. And I always do this for any type of epsilon delta proof. So I start off with the scratch work. And so what's my goal? My goal is to show somehow that f of x minus L, I need to show that this is less than epsilon. Okay? Now, what is it that we do know? Remember, we always have to assume our hypothesis is true. So before we actually do anything here, maybe we should add a note up here. This says note. So our assumption is the following. X minus a is always less than delta, always. So anytime I see an absolute value of x minus a, that is going to be less than delta. So that's actually our hypothesis we're assuming is true. We just need to show that f of x minus L is less than epsilon. So look at what happens here. By definition, what's f of x? Well, f of x, if I look at this example, if I go back up, it's defined as what? X to the x over 4 plus 3. So I could substitute in place of f of x, x over 4 plus 3. So that's my f of x. Minus whatever L is. And what's L? L is 9/2. So this is 9/2. So now what I'm going to do is I'm actually going to simplify a little bit here. If I simplify, what do I know? X over 4 plus 3 minus 9 over 2. I could combine the 3 and the negative 9 over 2. And if I combine them, what's 3 minus 9 over 2? That's actually going to be what? Negative 3 over 2. Okay? Are we okay with this so far? So, if I have this, now I could simplify this a little more. Now look at what happens here. I want to somehow get this to look like x minus a. And by the way, in this problem, what's a? A is 6. So here's what I know. Every time I see an x minus 6, I know that, so x minus 6 is less than delta, right? Because that's our hypothesis. Now instead of a, we have 6. So here's what I want to do. I want to get this to actually, I want to force out the x minus 6 out of this. Now, what do I know? Well, I want x to be alone, which what do I want? I want to factor out a 1/4 from this. But if I'm factoring out a 1/4, I have to factor out a 1/4 from the whole thing. So here's what I'm going to do. I'm going to say 1/4, if I factor that out, that'll be what? It'll be x minus, and if I factor out a fourth from 3/2, what does that become? That becomes actually 12 over 2, which is 6. Look at how convenient that is. And by the way, I could rewrite this as the absolute value of 1/4 times the absolute value of x minus 6. And the absolute value of 1/4 is what? That's just 1/4 times x minus 6. But look at how convenient this was. I forced out the absolute value of x minus 6. So what do I know? The absolute value of x minus 6 by default is less than delta. So then what does that mean? 1/4 absolute value of x minus 6 is less than 1/4 delta. Now remember, what was my goal? My goal was to show that f of x minus L is less than epsilon. So what is it that we want? We've shown so far that f of x minus L is less than 1/4 delta. And look, since it's up to me to pick the delta, here's what we want. We want 1/4 delta to equal to what? Epsilon, don't we? Because remember what I said? I want this to be less than epsilon. And I've gotten up to 1/4 delta. And since it's up to me to pick what I want delta to be, what does this mean? This implies, now I could solve for delta. We want delta to be 4 epsilon. So what does this show? This just says, look, whatever epsilon is, let delta be 4 times epsilon. Okay, and that's the key. Once I make that connection, now I'm ready to finish this off, or now I'm ready to start my official proof. But by the way, the official proof, you're going to notice, is pretty much going to have everything that I have in my Scratch work. So here's the official proof. So the official proof will start off like this. And these official proofs always start like this. So on the test, I'm guaranteeing you that you will have an epsilon delta question where you'll be proving a limit using the epsilon delta proof. So I want you to always write your official proof this way. So here's what we're going to say. Given epsilon greater than 0, and remember, for any epsilon, it's up to us to pick what delta is going to be. And we decided that we want delta to be 4 times epsilon. So we pick delta to be 4 epsilon. And if you still don't see why we picked delta to be 4 epsilon, hopefully once I go through the official proof, it'll make more sense. So here's what we're going to say. If absolute value of x minus 6 is less than delta, which remember, this is our condition that we're always assuming to be true. Now I need to show what? F of x minus L, this guy has to be less than epsilon. So then we could say the absolute value of f of x, which is x over 4 plus 3 minus 9/2. We need to show somehow that this is less than epsilon. So what do I know? This equals to what? X over 4 minus 3/2, right? Which is the same thing as what? If I factor out a 1/4 from it, which is x minus 6, notice how I'm basically, these steps, like from here on out, I'm basically rewriting my Scratch work, which that's the same thing as what? Absolute value of 1/4 times x minus 6, which is the same thing as 1/4 times x minus 6, which, by the way, 1/4 times absolute value of x minus 6 is what? Less than 1/4 delta. However, what's delta? What do we pick delta to be? We pick delta to be 4 times epsilon, which, let me continue that down here, which that equals to what? 1/4 times 4 epsilon, which 1/4 times 4 epsilon is epsilon. So look at what we just showed. We just showed that x over 4 plus 3 minus 9/2 is equivalent to all these things, but we don't care about that. This is less than epsilon. So what we could say is, so what we just finished it up with was, so absolute value of x over 4 plus 3 minus 9/2 is less than epsilon. whenever x minus 6 is less than delta. And that basically shows that this limit exists, okay? So hopefully you saw why we wanted to pick delta to be 4 epsilon. Because eventually my goal was to show that f of x minus L was less than epsilon, which, notice how I got the 1/4 delta, and the 1/4 delta times 4 epsilon gave me just epsilon. So that's how we pick what we want delta to be. But the answer is in your scratch work. That's basically where you could tell. Your official proof, if you look at it, 90% of it is just your scratch work back together, okay? But you need to make sure that you state this. If x minus 6 is less than delta, then you show that f of x minus L is less than epsilon, and then you're basically done. And it's also important to state epsilon's a positive number, and delta is 4 times epsilon. Okay, so that basically takes care of the definition, the precise definition of a limit.